So last week we talked about intermolecular forces. Alright. So we talked about two different types of intermolecular forces. So the first type is van der Waals force. I say that van der Waals forces can be further split into these two categories, but that's just for information. So I also mentioned that for van der Waals forces, the things that affects it, first is the number of electrons, second is the surface area. So for the number of electrons, right, this MR is a good indication of the number of electrons. So if let's say I give you two particular molecules, you just have to compare the molecular mass to know which one contains greater number of electrons. Alright. So the next thing that affects van der Waals is surface area. So a larger surface area gives rise to a greater surface area for the van der Waals force to act upon. And then the next intermolecular force of attraction that we talk about is hydrogen bonding. And I mentioned that only molecules which contains H bonded to F, O or N can undergo hydrogen bonding with another molecule of itself. So these are the two criteria. Alright. And then we look at some interesting properties molecules with hydrogen bonding can have, such as higher boiling points as well as lower density, as we have seen for ice. So today we'll be focusing more on the intermolecular forces. Alright. So first let's talk about simple molecular structure. So far we can see how atoms can combine to form stable structures. Alright. For example, all the structures over here, they are known as simple molecules. So simple molecules usually have the following properties. First, low melting and boiling point. Second, poor electrical conductivity. They have low melting and boiling point because we have mentioned that van der Waals force is very weak. So it's very easily broken. As well as the hydrogen bonding, they are also relatively weak compared to ionic bonds and metallic bonds. They are also poor electrical conductors because they do not contain any mobile electrons or ions to conduct. Whereas in the solid state, simple molecules such as iodine or water adopt a regular 3D structure with iodine or water molecules at the lattice points. So if you look at the structure below, alright, this is iodine. We know that iodine is a simple molecule. So when you decrease the temperature, iodine is going to freeze into a solid. So this is what the structure of iodine solid looks like. So all these are iodine molecules, and all these interactions, all these attractions, they are van der Waals force. Alright. So for explanation type of questions, please do not say attraction force or intermolecular force. Please use the correct terms such as van der Waals force, hydrogen bond. Because intermolecular force can mean van der Waals force as well as hydrogen bond, right? So you're not being specific. Same goes for attraction. So please use van der Waals force. Alright. Whereas for water, all of these are hydrogen bonds, like we have seen previously. So the iodine, water or water molecules, they are held together by van der Waals forces or hydrogen bonds. So this is what it's like in the solid form. What about in the liquid form, in the gaseous form? These van der Waals forces between iodine still exist, right? These hydrogen bonds between water still exist, just that it is not regularly arranged and they are weaker because the molecules are further apart. We have seen from kinetic particle theory. So some atoms can also combine with adjacent atoms to form giant molecular structures. And the main difference between simple molecular structure and giant molecular structure is that simple molecular structure is made up of individual molecules, whereas giant molecular structure is made up of an extended, or you can say infinite structure. So shown here are three examples. The first one is diamond. You should be able to spot it. The middle one is graphite. And the one on the right hand side is SiO2, alright, silicon dioxide, which is sand. So if you compare this solid structure with this solid structure, right, you will see some clear differences. Basically, for simple molecular structures, even if in the solid state you can isolate the individual molecules, right? What about the giant molecular structure? You can't, because all of them are connected together. You can't isolate any one of them. And basically, this is just one portion of the giant molecular structure. The actual one is actually extended out to infinity. The same goes for this and this. Alright. So can you suggest the following adopts a simple molecular structure or giant molecular structure? Do you know how to view this? This is the same as this. It's just another way of illustrating. This is the same as this is the same as this. Do you know why is it called an Olympicene?
Because the Olympic circles.
Yeah. I think this was prepared in year 2010 or something. It's called an Olympicene. For fun.
Looks like Olympics.
No, but why was it prepared?
For fun.
So fun.
To challenge what?
They build it for fun.
Yeah, they build it for fun. For example, this carbon nanobelt.
Oh, that looks cool.
No, because it's challenging.
Who
Alright.
makes it?
It's like saying, why do you want to build the world's tallest building instead of building many smaller buildings?
Oh, it's like Trump saying, I want to build a wall but never builds a wall.
Alright.
Well, the carbon nanobelt is so sure on the enemy.
It's all giant molecular.
So do you think these are giant molecular or simple molecular structure?
Actually, screw the first one. First one is simple. Second also simple. Third one giant. Or second one giant.
Wait, the second one is simple.
I believe it's simple. The first two simple, the last one giant. Oh wait.
Recall the definitions, alright? How do you determine if it's simple molecular or giant
No
molecular?
wait, the third one is simple, the first two are giant. I hope it's that way.
So, what do you define as a simple molecule?
Stable.
What is a simple molecule?
Atoms that combine to form stable structures.
Look at this. What are simple molecules? Simple molecules, they must have a discrete structure, right? How is this different from giant molecular structure?
Giant molecular expands.
It's made out of an extended or an infinite structure, correct? So is the first one discrete or infinite?
Infinite.
If you are saying infinite, that means there are other things connected together in a whole network. You can't isolate any of these. So is this simple or giant? This is simple, right? That's why students always get this wrong. Do you know why? They never seen such a big molecule before. They think that big molecules do not exist.
So my first answer was correct.
Alright?
And
Once again, this is a common misconception. Students always think that never learned before, don't exist. If you've never seen elephant before, elephant don't exist. If you've never seen giraffe personally with your eyes before, giraffe don't exist.
so that means
You
you've
must
never
see with
seen-
your own eyes.
So that means you've never seen shit with your own eyes, that means shit doesn't exist.
Yeah, correct. So is this simple? This is simple. Right. What about the one in the center?
Simple.
Is it discrete or is it extended out to infinity?
Extended out to.
It's also simple, right?
Oh wait, so legit my first answer was correct.
Then what about the last one, buckyball? Is this simple or giant? Why is it giant? Once again, ask yourself, is it extended? Do you understand the meaning of extended?
Can't they connect?
Do you understand the meaning of an extended network? For example, by extended network, for example, your phone is connected to an extended network around the world. How is it different from a discrete network? Discrete network means you connected to him, and maybe he connected to you. End of story. You are not connected anywhere to the world.
Means like if one 断掉, then the rest still can.
What do you mean? Yeah, still can. If you want to think about it that way.
Broken, but they are still
This
underwater.
will be known as discrete structures, right? If let's say you connected to 1,000 people, within these 1,000 people, they are not connected anywhere to the world, it's still called discrete. Understand?
Telegram.
As long as any one of you can link to the whole world, alright, it will be called extended structure. So for this case, do you think if let's say this atom over here can be connected to an infinitely far atom,
Yes.
If let's say I have another buckyball, do you think they can be connected?
I believe in the power of the
Cannot.
inner ones.
Cannot, right? So a buckyball is also a simple molecule. Alright? I purposely chose these three examples because I know that you will definitely choose the wrong answer. Because all of them seems big to you.
I chose that.
So none of them are giant molecular structures. So what are actually giant molecular structures? If you relook at diamond, if you draw an extended structure or infinite structure of diamond, basically what you're doing is that you are basically just connecting a lot of these together, right? Now, let's say we talk about this carbon atom over here. Is it connected to an infinitely far atom somewhere if you were to draw the extended structure? Yes, right? Now, the same goes for graphite and SiO2. But what about this case? If let's say you have another buckyball, basically what you're doing is that you're drawing another buckyball here and here and here. If let's say we talk about this atom, is it connected to this? Any atoms here or here or here? No, right? Same goes for this. If we draw another nanobelt, draw another nanobelt, draw another nanobelt. Is this particular atom connected to any one of them? No, right? Same goes for these. So they are all simple molecules. Hence, can you rank their boiling points from the lowest to the highest?
Lowest would be ODPC, then carbon nanobelt, then buckyball.
So which one? Like that.
Yeah.
That's their boiling point. Why is that so?
Buckyball most connected.
So previously we talked about the van der Waals force is affected by
Surface area
and size, right? So obviously buckyball would be larger than carbon nanobelt, larger than Olympicine. Alright, based on the number of atoms. So therefore, the boiling points is in this order. Alright. Why is that so? That's because buckyball
biggest surface area.
has a bigger electron cloud size, or you can say has more electrons than carbon nanobelt and Olympicine. Alright. Thus there it's greater extent of van der Waals forces between buckyball molecules. Alright. Hence greater
But why does it have bigger electron cloud size?
because its size is larger. Alright.
It's the biggest.
By inspection, buckyball contains more atoms than carbon nanobelts. Next, let's talk about giant molecular structure. Alright. So far we have seen a lot of giant structures. We have seen giant ionic lattice, giant metallic lattice, and giant molecular structure. So what's the difference between all of these? So basically for giant ionic lattice, we know that lattice particles, they will be cations and anions. Alright? And the ionic force is basically ionic bond. So what this means is that you can actually draw those kind of 3D cubes. Alright? Lattice points are those at the corners, as well as that we've seen previously at the faces and the center, etc. So all these are known as lattice points, and basically for giant any lattice structure, these lattice points contains cations and anions, and all these interactions, right, they are ionic bond. Whereas for giant metallic lattice, the lattice particles, they are cations, and the lattice force is actually metallic bond. So that's why we have giant metallic lattice as well, as we have seen in metallic bonding. And we also seen simple molecular lattice previously. So they can either be atoms or molecules. And the lattice force is basically intermolecular force of attraction, which consists of van der Waals or hydrogen bond, depending on which one we are talking about. And then we have hydrogen bonded lattices. And the lattice particles, they will be molecules. Of course, these molecules usually contain H something, HO, HF, HN, and the lattice force is hydrogen bonds. And lastly, giant molecular lattice. So for giant molecular lattice, all the lattice particles, they are atoms, and the lattice force is actually covalent bond. That's the difference between these 5 types of solid state structures. Alright. So this is like a summary of what we have done so far. So a giant molecular structure is formed by a large number of atoms covalently bonded to one another. The structure consists of a network of strong covalent bonds, which are significantly different from the weak van der Waals force that we have seen previously. So there are some characteristic examples which you will see, namely diamond and graphite. Alright? So diamond and graphite, they are known as allotropes. Have you heard of the term allotrope before?
Yeah.
So allotropes, basically they are different structures formed by the same element. So for example, diamond and graphite, they are allotropes. You have TiO2 as well, titanium dioxide. It can form a rutile structure and an anatase structure. They are also allotropes. For example, sulfur, you have phosphorus. You have white phosphorus and red phosphorus. They are also allotropes of each other. Right. So next, in diamond, each carbon atom is covalently bonded to 4 other atoms, tetrahedrally around it. Right? Why is it tetrahedral? We have seen this in VSEBR theory, right? If you have forgotten, you can always go back and take a look. So what properties does it have? So it has got very high melting and boiling point, very strong and hard, because all these strong covalent bonds, alright, require a lot of energy to break the strong covalent bonds. Take note, it's not van der Waals, it's covalent bonds. They are also insulators of heat and electricity. That's because all electrons are involved in bonding, no free electrons. And insoluble in all solvents, because all these strong covalent bonds cannot be broken easily by the solvents. So hence, giving rise to these properties. Likewise, silicon dioxide also adopts a similar structure. So you have to know how to draw silicon dioxide diamond. So how do you draw diamond? So for basically diamond, you just have to draw the tetrahedral shape. Alright. So this is how you draw diamond. Once you have this structure ready, you just extend out. Alright. Make sure these 3 are of equal length. And then how do you draw from here? Remember, you have to form a hexagon. So this is a hexagon, this is another hexagon. Alright. And then so on basically. Alright. This is how you draw structures of diamond. So how do you draw silicon dioxide? So for silicon dioxide, take note. After you have drawn the structure of diamond, you just have to draw another atom between the bonds, and that will be silicon dioxide. Alright, and so on. So that's how you convert diamond to silicon dioxide. Maybe I draw wrong. If I were to draw it nicely, see whether I can draw it freehand.
Artist coming out already.
Etc. Alright.
The artist is coming.
You want to draw in a nicer way. If you draw like that, people know that you are chemist. If you draw just now, they know that you are a student. So this is the structure of diamond and silicon dioxide. And how do you draw silicon dioxide? So in silicon dioxide, each silicon atom is covalently bonded to 4 oxygen atoms tetrahedrally. Alright, take note. Silicon dioxide, its formula is SiO2. So a lot of students think that one silicon is bonded to 2 oxygen. This is not true. Alright, one silicon is actually bonded to 4 oxygen atoms. You can think of it as the sodium chloride case. Remember, for sodium chloride, when we did ionic bonding, we mentioned that each sodium is surrounded by how many Cl? 6, right? But that doesn't mean it's NaCl6. How do you derive SiO2? Basically, it's derived in the same way as how you derive the formula of NaCl. You just draw a box and count how many silicon there are, how many oxygen there are. Alright? It is independent of how many oxygen is bonded to one silicon. So this magic number 4, alright, that's how they derive it. So each oxygen is bonded to 2 silicon atoms, and the arrangement of silicon atoms in quartz is similar to that of diamond. Alright, and I already taught you how to interconvert. So next one, silicon and silicon carbide also forms giant molecular lattice structures, but they have a lower melting point than diamond. So why do you think so? So how do you draw a structure of silicon and silicon carbide? If I tell you that they also form giant molecular lattice structures. So if you look at the periodic table, silicon is below carbon, right? So I expect them to form the same kind of structure. So basically you just have to draw the same thing, right? And you can extend it out. Right, and so on. So each of these is a silicon, right, instead of a carbon. So that's the structure of silicon. Think about silicon carbide. How do you draw silicon carbide? How do you draw silicon carbide?
Similar, but then just add one carbon.
Is this correct?
Yeah.
Wait, don't copy this. Is this correct or not?
No,
By adding carbon here.
no.
Why not?
It's too many carbons.
Look at the structure of SiO2. For SiO2, you adopt this kind of structure, alright, whereby you have 2 oxygen, that's why you insert it in between your bonds. But here you only have 1 carbon. So what do you think you should do?
Extend it out.
You just have to replace, for every 2, you just have to replace 1 with carbon, right? Isn't it? Correct, right? In other words, he adopts the same structure, just that 50% of the atoms are carbon, 50% of the atoms are silicon. we are only 50% done. The question asks which one has why do they have a lower melting point than diamond? So why do you think so? Now, if let's say you really want to break a giant molecular lattice structure, what are you actually breaking when you increase the temperature? Do you break van der Waals laws?
No.
Then what do you break?
Covalent bonds.
What do you break? What do you break? I say that if let's say you really want to, let's say, melt diamond, alright, what forces are you breaking when you melt it? Covalent bond, right? When you want to melt, let's say, ice, you are breaking hydrogen bonds. Are you breaking covalent bonds in ice? No. What about when you want to melt, when you want to boil water, do you break the covalent bonds between hydrogen and oxygen? No. You are still breaking hydrogen bonds. But for this case, if you are melting diamond, you are breaking the covalent bonds, right? So the same goes for this. You are breaking this, alright, and this. So what can you tell me about how difficult it is to break these bonds compared to diamond? Basically, you are comparing the ease of breaking a Si-Si bond for silicon versus Si-C bond for silicon carbide versus C-C bond, right? So which one do you think is easier to break? Because?
Less small electrons.
We have learned this in the front part. If you have forgotten, please go back and refer.
So this one is a small electron cloud, so the covalent bonds are weaker, therefore it's smaller extent.
So which part have we learned about this?
We didn't keep the concept.
Don't remember?
Is it this one?
Wow, you don't even go back and revise. So if test, then sorry because I already gave you whatever, alright? Gave you an encyclopedia, but you don't want to use the encyclopedia. Look at this, bond energy, alright? What affects bond energy? First, bond order. The 3 bonds that we talk about, they all are single bonds, so we don't use these. What about atomic size? I give you specifically the 3 examples, right? Chlorine, bromine, iodine. Now it's just comparing Si, Si and Cc. So if you compare these two, what can you say? Si involves a larger orbital overlap, right? So larger orbitals are weaker, right? Because they are more diffuse, so the overlap is less effective, which means the Si bond is weaker, right? So it's exactly this sentence. What about Si-C bond compared to Cc bond? Then you'll be in between, correct or not? You are changing one atom to silicon, which means this effect still happens, just that it's not as prominent as that of Si-Si. Understand? So therefore, alright, the trend is basically like this. Alright, this is stronger than this, stronger than this. You can put a note here, revise, page, don't know what, previously. It's all on that page. So not that difficult, right, actually. You are just basically making use of bond energy. So the next giant molecular structure that we are going to talk about is actually graphite, which is another allotrope of diamond. So graphite is made of flat layers of carbon atoms arranged hexagonally. Within the layer, each carbon atom is covalently bonded to 3 other carbon atoms using 3 of the valence electrons, and the 4th electron is not bonded and is delocalized throughout the layer. Alright, if you look at the structure on the left hand side, you can see that basically within the layer there exist strong covalent bonds, whereas between the layers there exist weak van der Waals forces. So for graphite, alright, it's kind of similar to your simple molecules. Within that simple molecule, it consists of strong covalent bonds, and between molecules there exists weak van der Waals force. Right? And this is how you draw this structure. Please learn how to draw a structure. You will be asked on how to draw such structures. So how do you draw such structure? Basically, you just have to start off with one hexagon, and then basically you just extend out. Alright? Extend out. Like how you draw the honeycomb structure. Alright? So each of these is a carbon. Carbon, etc. So you can see that each carbon is covalently bonded to 3 other atoms. And basically there's another electron left in the p orbital of carbon. Alright, each of these carbon, there's one electron that's left unbonded. So what can happen is that these electrons can overlap sideways with this carbon to form something like a double bond. Alright, something like a double bond, and so on. So there's an extended network of double bonds. Or it can form a double bond with the neighbor on its left. Basically, there are 3 places whereby it can form a double bond. So it can either form here, or here, or here. So what this means is that this allows this electron to be shared almost with its neighbors equally, and such a sharing causes what we call a pi electron cloud above and below each layer of carbon atoms. So this electron actually facilitates electron transport from one end to the other end. So as I've mentioned, the attraction within each layer is covalent bonds. But the attraction between different layers is due to van der Waals forces. Alright? Oh, by the way, this one you don't have to know. sp2 hybridized. Only for advanced students. So this is how you draw the structure of graphite. And one more thing for you to think about. Alright? Although it is not very obvious and not explicitly asked, if you look at the layer on the top and the layer below, what do you realize?
Yeah,
Are they identical? So why are they not identical? Look at these also. They are not identical, this and this.
yeah.
These and these are identical. Alright. So why do they like to, alternate in terms of
Repulsion.
arrangement? So what about repulsion?
Because it is exactly the same, that's the same, like the same charge ones will repel each other, causing them to be like change.
What do you think? Think of it this way. If let's say you have 9 ping pong balls, let's say, all stuck together, right, in one layer, and then you have another 9 ping pong balls stuck together in one layer. Alright? Now, if you were to stack this on top of this, what do you think is the most likely arrangement?
One row.
If you look from the side, will it be like that?
No.
Or will you prefer to be like this? A or B?
B.
B, right? So the same goes for carbon atoms. Alright? Why? That's because if you pack it like that, there will be repulsion. Imagine all of these are carbon atoms. There will be some form of repulsion between these two, right? Compared to this case. Compared to this case whereby, the one on top is just nice lying in the space. Whereas the one in the bottom just nice lies in the space in the top. So there's less repulsion. So hence, he adopts this kind of alternating structure. Alright? Yeah. So some properties, this is just some interesting fact. You can go and flex to your friends. You can first ask them, do you know how to draw the structure of graphite? You purposely let him draw a wrong one, then you correct him. You say, my tutor said this. You don't know, right? Then go and attend his class.
So that means, right, when you draw this, like if they ask you to draw it, you draw this, and then the second one you need to alternate.
Most likely you won't need to draw the second one. But for the second one, if you alternate or don't alternate, it doesn't matter. Because I already mentioned that that's like a trivial fact. Alright, most likely you will not be penalized based on that because you are not taught that.
But then if you join, the teacher will be impressed.
So some properties, they have high melting and boiling points. Some teachers don't even realize that by now, by the way. Alright, they think that, just one layer.
Okay.
Anyways, they have high melting and boiling points because if you are trying to melt the graphite, you are also actually trying to break these covalent bonds, as well as very, very strong van der Waals force. They're also good conductors of electricity. That's because of the delocalization of mobile electrons. So in graphite, there's actually mobile electrons, which allows electrical conductivity. That's why your pencil, which is graphite, can conduct electricity. They're also soft and slippery. That's because the layers are held by weak van der Waals force, which can slide over one another easily. That's why when you write using a pencil, the graphite, can be detached from a pencil onto the paper.
Because of friction.
Yeah, you are not overcoming the covalent bond. You're only overcoming the van der Waals force. Alright. So here's a table for you to summarize and compare the differences between a diamond and graphite. So in terms of structure, both diamond and graphite, they are giant molecular structure, right? Giant molecular structure. So what about melting point? Diamond is high, graphite is also high. If you want to, ask me which one is higher, I also don't know. It really depends on. There are different kinds of graphite as well.
Is it true that it's like above 3,000?
Yeah, it's above 3,000 definitely, but 3,000 what? Nobody knows.
Why?
In fact, even if you Google the melting point of diamond and graphite, there are some variations as well.
Because my schoolmates like memorized there's 3,000.
Yeah, but most of the time it's above 3,000. Alright, you can go and Google, you won't find an exact value. It depends on the purity as well as some other factors. Alright, electrical conductivity, diamond do not conduct electricity or heat, whereas graphite does conduct electricity and heat. Hardness wise, diamond is hard, hard and strong,
Soft and
whereas graphite is soft and slippery. There's a similarity between them and as well as the differences. Alright? So this is the end of covalent bonding. We have been going through it for the past few weeks. Alright? So for now, can you please attempt the true false questions again? I hope you brought the questions. The in-class as well as the homework questions. First one, the electronegativity increases across period down the group.
false.
False, right? It should be up the group. Alright. CH bond is a non-polar covalent bond. True, we have seen. A dative bond is weaker than a covalent bond. False. I mentioned that dative bond is exactly the same as covalent bond. It's just how you represent it. Oxygen has a valency of 2. True, right? Oxygen forms 2 bonds. Correct?
Oh wait,
So it has a valency of 2.
not valency.
This is not valence electrons, this is valency. Valency means how many bonds it tend to form. I really thought about it in one of the pages. Both ionic and covalent bonds are present in ammonium nitrate. True, right? Ammonium nitrate has the formula NH4NO3. So between this NH4 and NO3, there exists there is ionic interaction, and within each of them there is covalent bond, right? So I've illustrated this previously as well. The covalent bond in hydrogen is formed by head-on overlap of 2 1s orbitals. This is true. Pi bonds can be formed by sp overlap. False. It can only be formed by pp. Sigma bonds are stronger than pi bonds. True. You have seen it because it's head-on. CC double bond is twice as strong as CC single bond. False. We have seen that pi bond is weaker. CO bond is stronger than CF bond.
False.
False. CF bond is stronger because CF bond is more polar. So therefore, the delta plus delta minus is bigger. Hence, the electrostatic force between these two are stronger. If you are unsure, you can refer to the bond energy section. The bond angle of ammonia is 107 degrees. True. Alright. There are only 4 that you have to know: CO2, methane, ammonia, water, as well as their bond angle. CO2 is 180, methane is 109.5, ammonia is 107, water is 105. H2O has a larger bond angle than F2O. True, right? We have seen this as well. We have mentioned that for OH2 and OF2, alright, F is more electronegative than O, so electrons are closer to F. For this case, it will be closer to O. If it's closer to O, that means they are closer to each other, repel each other more strongly, hence greater bond angle. Van der Waals forces are stronger between iodine than bromine molecules. This is true, right? Because iodine, they are bigger. Another thing to take note, between iodine molecules, Van der Waals forces are stronger than bromine, but the covalent bonds of iodine, alright, between two ion atoms, they are weaker than that of bromine. So the covalent bond strength has nothing got to do with the Van der Waals force. Alright. During melting of ice, covalent bonds are broken. False. So what bonds are broken? Hydrogen bonds. During melting of sand, covalent bonds are broken. True. Because sand adopts giant molecular structure, which means that you have to break the covalent bonds. The only type of intermolecular force of attraction that exists between water is hydrogen bonding. False. Remember, I mentioned previously, Van der Waals force exists between all molecules. Just that which one is more dominant? Is it hydrogen bond or Van der Waals? For water, hydrogen bonding is more dominant. In the crystal structure of ice, each oxygen atom is surrounded by 4 hydrogen atoms. True. So among these 4 hydrogen atoms, 2 are hydrogen bonds, 2 are covalent bonds. You can refer to the section on ice structure. The hydrogen bonds between water are stronger than ammonia, than between that of ammonia. Is this true or false? True, right? I mentioned a few factors which affects hydrogen bond strength. This is one. HF hydrogen bond is stronger than HO, is stronger than HN, according to their electronegativity. In SiO2 giant structure, each silicon is surrounded by 2 oxygen atoms. False, right? I just mentioned that you cannot just rely on this structure for giant and extended structures like sodium chloride, etc. You have to recall what I told you just now, alright? Simple molecules can form lattice structures. True, in the solid state. In the solid state, either atoms or molecules occupy the lattice points, and the attraction is intermolecular force, which is Van der Waals. Diamonds have higher melting point than graphite. This is not true, alright? It is not true.
But you said,
I mentioned that it's very hard to compare. Both of them are high. Alright? So it's not true to say that diamonds have higher melting points. In fact, I think graphite should have the higher melting point.
that's why I said leave it blank. Isn't that be the more logical?
And the next one, the boiling points follow the order H2O smaller than H2S smaller than H2SE. True or false?
True.
False. Remember, H2O has got hydrogen bonds, right? Whereas these two, Van der Waals. Now, between these two, which has got Van der Waals, H2SE should have a higher boiling point because it's larger. Correct? So therefore, you would expect the boiling point to be H2S, H2SE, and then H2O. This is what you expect.